Hello everyone, welcome back again. So in this video, we will be solving one problem based on the theories taught on the previous video. So let us go through the problem. Calculate the safe load that can be carried by a connection shown in the figure below. The figure is below. Uh, the figure consists of HSFG bolt, high strength fixing grip bolt of grade 8.8 with 16 diameter. Assume the thickness of bracket plate as 12 thick and the column used is ISWB 350. ISWB 350 Indian Standard Wide Flange Beam 350. The overall depth of the beam is 350. Assume no slip condition and the coefficient of friction is given as 0.5. So data given for us is that the diameter of the bolt is 16 the grade of the HSFG bolt is 8.8, and the column is ISWE 350. Now this is the figure. This is the column. This is ISWB beam of 350. This is the bracket of thickness 12 Okay, there are 6 number of bolt and pitch for the bolts are kept as 50 and edge distance is 40 and gauge distance is 100 So from the center of the beam, the center of the bolt connection, the distance of this bolt from the center is 50 and on this side also 50 Okay. Now to find the shear strength of the bolt, it's a HSFG bolt, so the shear strength will be governed by slip resistance of the bolt. And as in previous video we have seen, the shear strength of the HSFG bolt can be found from clause number 10.4.3 of IS 800 2007. So let us go and check. See clause number 10.4.3 where you can see the formula for shear strength of HSFG bolt is given as mu f into Ne into Kh F0. F0 is the proof load, Kh is a constant, depends on clearance hole, Ne is the number of slane plane, and mu f is the coefficient of friction that is given as 0.5 for this problem. Okay, so we'll directly go to the problem and find out is the value. Mu f is given in 0.5 in this problem. Ne will assume as 1, Kh equal to 1, and proof load. Proof load is nothing but the multiplication of 0.7 FUB into A and B. A and B is the net area of the bolt, and that we have found out here already. So A and B is this value 0.7 into pi by 4 into d square. So this is the gross area of the bolt. By multiplying with 0.7, we will get the net area, and FUB as the bolt grade is 8.8. So FUB will be the 100 times of this value, so it will be 800, and so by this we will get a value of 87.82 kilonewton as proof load. So by simply placing this value, we will get the slip resistance of this bolt as 35.13 kilonewton. Now we have to check its bearing strength to get the bolt value, and we will use the minimum value of these two criteria as its bolt value. Now bearing strength, we know we are familiar with this formula, 2.5 kb dt Fu by gamma mb. And kb is a constant that depends on these criteria. So based on the given data, you can find E value is given as 40. D0 is the nominal hole diameter. The hole diameter is 16. So the hole diameter will be 18. By putting all this value, we will get a minimum value of kb equal to 0.67. So if we replace this value with 67, we will find the value of bearing strength. One thing we have to note, this T is the minimum thickness of the bracket and the column flange. Now this bracket thickness is given as 12 mm in the problem, but the flange thickness of ISWB is 11.4 mm, that we can see from IS SP6 on page number 4. We can get the value as ISWB. See, the thickness of the flange is 11.4 mm, which is less than 12 mm. So we have to use 11.4 mm to find the bearing strength of this bolt. So we will be using 11.4 for T. Okay, 11.4, the bolt diameter is 16 fu, the ultimate strength is 410, and M gamma MB is 1.25. So by placing all these value, we'll get a value of 100.21 kilonewton. So we got the slip resistance shear strength as 35.13 and the bearing strength as 100.21. So bolt value will be minimum of this two, that will be 35.13 kilonewton. Now we have derived the bolt value of the HSFG bolt. Now directly we will go on to calculate the forces on the bolt due to moment and direct force due to the load coming onto the bolt. Now to calculate the forces due to moment, we have to find the radial distance of each bolt. So this R1 represents bolt number 1. That is, if we see the figure, so here the column was like this. There are 6 bolts. The CG of this was passing like this. Okay, this distance was given as 50. Okay, and this distance was given as 50. Okay, so for this bolt, this is the number 1 bolt. This distance will be R1. Okay, so this is how we can calculate this. This will be this distance square plus this distance square. Okay, so by simply doing that, we get a value of 70.71. This is the number 1 bolt. This will be number 2. Okay, so number 2, the radial distance of second bolt from the centroid of the bolt group will be simply this value. This will be simply 50, and this value will be equal to this value as well. So simply you can number them 3, 4, 5, 6. Now for radial distance of number 1 bolt, number 3 bolt, number 4, number 6 will be equal. So this written over here, the radial distance of R1, R3, R4, R6 will be same, and that value will be 70.71. And radial distance of R2, bolt number 2 and bolt number 5 will be same, that will be directly equal to 50 mm. Okay, now to find the summation of R square, we can simply replace R3, R4, R6 by simply R1. So that will be 4R1 square plus R2 square plus R5 square. Since R2 and R5 are same, so you can write 2R2 square. And by doing so, you'll get a value of 25000 mm square. This is the summation of R square. Now we simply use this. Okay, now in previous video we have seen the forces on any bolt due to moment is equal to mt dot radial distance by summation of r square. This is the total moment. Total moment will equal to load multiplied by eccentricity. So mt is simply replaced with p into e, and since we are calculating for first bolt, so we have a subscript of 1, so the radial distance will be using r1, and summation of r square we have already found out. So since we have to find the safe load, so p we have to find E is given as 150 mm, R1 is 70.71, and this value we have found out as 25000. So we'll get a value of 0.424 P. Okay, and we have to find the axial force on bolt since a load of P is coming and 6 number of bolts. So every bolt will experience a direct force of P by 6. Okay, so the forces on first bolt will be a axial force of P by 6, and force due to moment will be 0.424 P. Okay. Now, since we do not know this is the critical bolt, we have to find which is the critical bolt. And for that, we can simply calculate the forces on every bolt, or we can take a little time to find what can be the critical bolt. Simply we can draw one figure and we can find it. Since see there are 6 bolts, okay, and since we know the direct axial force will be same for all bolts, the only thing that varies is the force due to moment, and force due to moment is proportional to the radial distance from the centroid of bolt group. And as we have seen just earlier, that the radial distance of this bolt, this bolt, and this bolt are same. So the force due to moment on these 4 bolts will be same. And since the direct force is same for all, so this all 3 or 4 bolt will have same force on them, and this bolt and this bolt will have same force on them. So we can simply find the forces on bolt number 1 and bolt number 2, and we do not need to find forces on every bolt since the force on this bolt, this bolt, this bolt, this bolt will be same, and forces on this bolt will be same. So simply we can find force on bolt 1 and bolt 2, and we will be able to find the critical bolt. Okay, so we have just done that. And similarly, as we have calculated force on first bolt due to moment as 0.424 P, similarly we can find force on second bolt due to moment as P into E into radial distance R2 we have found out as 50 mm, and summation of R square is 25000, that is coming out to be 0.3 P. Okay, now since for the first bolt the two forces are making an angle of theta, so we have to take the vector sum to calculate the resultant force due to direct axial force and force due to moment. But for the second bolt, since we are seeing that the direction for axial force and the force due to moment are in same direction, so we do not have to take the vector sum, we can simply take the scalar sum, that is resultant force on bolt 2 will be Fa plus Fm, but for bolt 1 we have to take the vector sum, and to calculate the vector sum we have to calculate the angle between the direct axial force and the force due to moment, and that we can simply find out by simply from this diagram. This is the bolt 1, this pitch was 50 and this was 50, so tan theta will be 50 by 50, so theta 1 will be tan inverse 50 by 50, that will be 45 degree. So by using this theta we can calculate the resultant force on bolt 1. So that is if m1 square if a square plus 2f m1 into fa into cos theta. So we have found out these values earlier. So the resultant force on bolt 1 will be 0.5074 P. Okay, and similarly for bolt 2, simply we can take the scalar sum Fa plus Fm2. Fa is P by 6, that is same for all bolt, and Fm2 force due to moment on bolt 2, just we have calculated, it is coming out to be zero point 0.3. So the resultant force on bolt 2 is 0.466p. So two bolts, if bolt 1 and bolt 2, we have found out their resultant force. So the to carry the to decide what will be the safest load, we have to take the maximum between these two values. The maximum load coming on bolt 1, that is 0.5074p. So this is the amount of force a bolt, the critical bolt, is experiencing. So the load has to satisfy this condition. So we'll simply equate this force on resultant force on bolt with the bolt value to find the safest load that can be applied on this joint. Similarly, so the bolt value earlier we have found out as 35.13, and a critical bolt is experiencing a bolt for a force of 0.5074p. So by this equation we can simply find the amount of safe load, that is coming out to 69.23, approximately we can say 60 kilonewton, 69 kilonewton. So for this connection we can simply apply a force of here 69 kilonewton without failing. Okay, I hope this problem is clear. Okay, thank you.